Now that we are familiar with the parent functions and their corresponding graphs, we will next examine how an operation in one of those basic functions affects the graph. We're going to look at vertical stretching and shrinking, reflections, and horizontal and vertical transformations. Let's start with 3.3.2 vertical stretching. First, we're going to assume that f of x represents one of those 6 basic parent functions. It could be the y equals x squared quadratic function. It could be y equals absolute value of x. So f of x represents any one of those 6 basic functions. Now, we're going to see what happens to the graph if I multiply that function by a constant. Well, it kind of depends on the size of the constant. If that constant a is bigger than 1, then the graph of y equals a times f of x is called a vertical stretch of the graph of y equals f of x. For example, if I consider y equals 2x squared, well, the parent function there is the x squared quadratic function, or the parabola. This particular graph would be twice as tall as the original parabola, so it's going to stretch away from the x-axis. On the other hand, if the constant that I'm multiplying by is a fraction between 0 and 1, then the graph of a times f of x is called a vertical shrink of the graph of y equals f of x. For example, y equals 1/2 x squared. This parabola is going to be shorter or closer to the x-axis than the original function. Where 2x squared is a tall, skinny parabola, 1/2 x squared is a much wider parabola. But they both share the same fundamental nature of the parent function, y equals x squared. The next transformation that we'll consider has to do with the introduction of a negative sign in a particular position. 3.3.3 is describing reflections. So again, we're letting f of x represent one of our elementary functions, and we're going to consider what happens to the function if I multiply by a negative 1 on the outside, and what happens to the function if I multiply the argument by a negative 1. Y equals negative f of x reflects the graph of y equals f of x across the x-axis. For example, if I look at negative square root of x, it's the reflection of the original function across the x-axis. So whereas y equals square root of x, let me draw the parent function out here for a visual. Square root of x does something like this. Negative square root of x reflects across the x-axis. So negative square root of x is going to open like this. It's still the same basic nature as the parent function. It's just opening in a different direction. If, however, I put the negative inside the argument of the function, f of negative x, this is going to reflect the graph across the y-axis. For example, y equals square root of negative x. So I'm going to look at the original parent function and reflect it across the y-axis. It's still half of a sideways parabola, but now it opens to the left. So these are called reflections. Now, let me pick your brain. Is that negative under the radical bothering anyone? It might bother you because we've been saying you can't have a negative under the radical. That'll give you an imaginary number, and we can't plot an imaginary number in the plane. Why can we do it with a function? Well, if I look at this green function over here and I read the domain would be negative infinity to 0. The leftmost x value, well, it keeps going to the left forever. The rightmost x value is right there at the origin. So the domain is negative infinity to 0. Well, how do I interpret that? This means I can only plug in negative numbers or 0, right? Well, if I plug in a negative number for x, I've already got the negative from the function. If I plug in a negative, do you see how that double negative actually does give me a positive radicand? and I will get a positive number out, a real number out. So the rule of thumb is it's okay to have a negative with a variable under a radical. We just can't have a negative constant under the radical. Maybe that wasn't bothering you at all, but if it was, I hope that clears it up a bit. So if the negative is outside the function, as in this case, we're going to reflect across the x-axis. Okay, if I consider going from, here's just a way to remember this, if y was equal to something positive and now y is equal to something negative, well, it has changed sign. It has been reflected across the x-axis. Whereas here, if I go from positive x to negative x, if x changes sign, then that causes me to reflect across the y-axis. Okay? So you so far have vertical stretch and shrink. That comes from multiplying one of those basic functions by a constant. And now we have negatives, a negative outside the function or inside the function. And by inside the function, I mean under a square root, inside absolute values, under a cube or other exponent, something like that. The last two that we're going to look at, 3.3.4, vertical and horizontal transformations. These are the easiest ones to carry out by hand. If f of x represents some basic elementary function, then y equals f of x plus k, where k is a constant. We're going to shift the graph of f of x up the y-axis by k units. For example, y equals the absolute value of x plus 2. That's going to look like my original v parent function, but it's going to be shifted up the y-axis by 2 units. If, however, I subtract a constant from the original function, like f of x minus k, then we're going to shift the graph of f of x. Can you figure out which way we're going to go this time? If plus k means up the y-axis, minus k must mean what? Down by k units. So for example, y equals absolute value of x minus 2. That's going to be our basic V shape, but it's just shifted down the y-axis. So kiddo grows up and moves out, right? Now, those are vertical transformations. Horizontal transformations are a little bit more of a brain teaser because it doesn't always follow your intuition. Notice in the vertical transformation, the plus k or the minus k was outside the function. It was not part of the absolute value. It was just hanging out by itself in the cold. However, if the constant is inside those absolute value bars or under a square or under a radical, then it's going to be a horizontal transformation. So again, if I have a constant that is part of the argument, like f of x plus h, we're going to shift the graph of f of x. Now, the plus, this is a horizontal transformation, so we're talking about left and right transformations. When you see the plus, your brain's going to want to say, oh, that goes to the right, but actually it's the opposite. This one is going to go left. For example, y equals the absolute value of x plus 2. That's going to be my original v, absolute value function, shifted left by 2 units. Okay, so you have to remember when it's inside the function, it goes the opposite way of what your intuition is going to tell you. Well, if plus h inside the function goes to the left, if I have f of x minus h, which way do you think it's going to go this time? Hopefully you see the pattern and you can say it's going to go right. For example, y equals the absolute value of x minus 2. Now, please compare this example and this example. Notice the placement of the constant. If it's outside the function, it's going to be a vertical transformation. If it is inside the function, in this case, inside the absolute value bars, it's going to be a horizontal transformation. The same thing is true for this other pair that we have. Those are similar, but here the minus 2 is inside the function, so it's going to be a shift to the right. Whereas in this case, the minus 2 is outside the function, so it is going to shift down. The good news about all of these transformations is if you feel doubtful or you don't feel confident, you'll be able to back it up with your calculator. So let's practice recognizing transformations. Example 2, identify the parent function and the transformations. So we did this in the last video. We want to figure out who's the daddy, right? Who is the parent function? In this case, we have y equals 3x squared. That corresponds to the parent function y equals x squared. Let me go ahead and label that as the parent function. But this function is multiplied by 3. So this multiplier represents a vertical stretch. So our transformation is to stretch by a factor of 3. So I'm going to have my original x squared function. This guy is going to be taller and skinnier. So that's when your kid grows up and is taller than you, right? Example B, we have y equals 1/3 times the absolute value of x. First, we're going to identify the parent function. Again, when you identify the parent function, you're ignoring all the details there. You're saying, what's the fundamental nature of that graph? The parent of this graph is absolute value of x, the v shape. Since this one is multiplied by a fraction, which is less than 1, this is going to be a shrink by a factor of 1/3. And I'll show you how to execute that on a graph. So it's going to shrink towards the x-axis. That means it's going to be a little bit wider or not quite as tall as the original function. So this is when your kid grows up but didn't quite make it as tall as you. Let's look at example C. The parent function here is, can you figure it out? Square root. That's the basic nature of the graph, but we have a negative outside the function. If the negative is outside the function, this means we're going to reflect across. Now look, we're going from y equal to a positive value to y equal to a negative value. If y changes sign, that means we have reflected across the x-axis. If you can really learn that, it'll stick with you better than just memorizing it. Whoops. Next example, y equals x squared minus 6. Who's the daddy on this one? The parent function is y equals x squared. So this is going to be a parabola shape. Now let's interpret the operation. We are subtracting 6 outside the function. That means this is going to be a vertical transformation. Do you think this is going to go up or down? This one is going to shift down by 6 units. Did you get it right? Oops. Shift down by 6 units. Next example, y equals x plus 6. This one is so basic you could probably graph it without even thinking about transformations. Who's the parent function on this one? The parent function is our identity function, or our most basic linear function. But we are adding 6. This is a vertical transformation. Will this go up or down? This one shifts up 6 units. Okay, so it's kind of a new way of thinking about your basic linear function. You have learned to graph mx plus b. So notice our y-intercept is 6, our slope is 1, so you could graph it with that perspective, or you could say this is a line that has been shifted up the y-axis by 6 units. Notice we're just shifting our y-intercept up to 6. Next example, who is the parent function on this one? Ignore the details, look at the main operation. This is our cubic function, or our vertical squiggle. Now, notice we have a minus 2 inside the function. That means it's under that cube. So this is going to be a horizontal transformation. Should we shift to the left or to the right? In this case, we're going to shift right by 2 units. Remember, with the horizontal transformation, it goes the opposite way of what your intuition thinks. Negative usually means go left, but it's the opposite. We're going to go right. Let's look at x plus 2 quantity cubed. So we're still looking at the same parent function. These guys are siblings. Whereas x minus 2 went to the right, where do you think x plus 2 cubed is going to go? This one is going to go left. So these two kiddos grew up. One moved east and the other one moved west. The last one we have here is a cube root function. So we're thinking this time about our sideways squiggle. And notice in this case, the negative is inside the function. Now, if you look closely at the way we have it written, notice here x is positive, here x is negative. So you could say x has changed sign. If x changes sign, then we reflect across the y-axis. Okay, so now that we have recognized parent functions, we have a basic idea of their graphs, and now we know what the transformations are, we actually want to apply these to graphing more complicated functions. In some cases, if you glance down here at these examples, you've got more than one transformation on one function. So what we want to do is recognize the parent function, and we want to figure out what all the transformations are and then execute them in the proper order. So the first thing that you'll want to do is stretch or shrink if you have a multiplier. Then reflect, if it's present, across x or y axis, and then we'll take care of vertical and horizontal transformations. All right, I will work all the examples in the next video, so take a break if you need to, and we will resume with the examples next.